Okay, I've got 3:59, but we will go ahead and start anyway. Let me make sure I've got this thing running and recording. Okay, looks like it is. Okay. All righty. So I should have Google Chrome up with the slides presentation from today. If that's not showing, let me know. Uh, in theory, this works. Uh, Today, after the detour last week into some useful applications of Python, um, we're going to go into a more computer science week where actually last 2 weeks we'll be talking about some fairly interesting technologies about how computers work and solve problems. Today's topic is non-base 10 numbering systems, binary, which is base 2, and hexadecimal, which is base 16. Standard administrative announcements. Lab 10 will be released tonight. It's due Thursday night. I need to debug it before I assigned it. I found a bug in it at about 3 o'clock that I need to fix. I was originally going to release Project 3 today. It will now be released on Wednesday, so you actually have a day or two without an assignment hanging over your head. It will be due that last week of class. Originally, it was going to be Monday the 11th. We'll see how it goes. Remember that Monday the 11th is the last actual class day. The final exam is Friday night the 15th. Project 2 and Homework 6 are both due tonight. Here are the submit commands for them. As far as I know, submissions are working for both of those. If you need an extension, you need to ping me quickly. There's one or two students have already talked to me. If there's a legitimate reason, we could do an extension, but we need to get these in so we can get things back. All right, now on to today's lecture material. Humans count to things by powers of 10, what we call 10. 10, 100, 1,000. Why? Because most humans have 10 digits, 10 fingers, 10 toes. Yes, there are people who don't, but those are rare. The vast majority of humans have 10 fingers, 10 toes. And it was very easy to keep track of things. You know, you counted on your fingers. When you got all 10 fingers, you wrote down a 1 and started again. And that was the basis for our counting system. And that's why this is called the base 10 or decimal system for counting. We have these 10 symbols, which we call digits, that are used to count 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. And every number that can be represented in the human decimal system can be represented using only these 10 things, 0 through 9, in some combination or with some commas or some decimal points or whatever else thrown in. But those are the only digits. It turns out that while that's the best way for humans to count, it is not the best way for machines to count. Computers, the original one, and most of them since, are in effect made up of electrical switches. You may hear that if you've taken computer architecture, you may hear the term flip-flop. It's an electrical switch that has two states, on or off. Either electrical current flows or electrical current doesn't flow. Those were the original ones. Nowadays, it's usually electrical voltage is maintained of one of two states. You don't actually let it go to off. You have a positive voltage or a negative voltage. And these electrical switches, as I said, have really only two states, which we effectively call on or off. On is something that we say has the value 1, and off has the value 0. And this is what's called binary systems. You only need two digits, 0 and 1, to represent all numbers using powers of 2. So there's only the two binary digits, 0 and 1. But back in the early days of computers, long before my time, binary digit was a pain in the neck to say all the time. So computer scientists being lazy, binary digit got shortened to bit. And that's where we get the term bit. A bit is short for binary digit. There's the old joke. There are 10 types of people in the world, those who understand binary and those who don't. I'm sorry, it's a bad joke. Computer scientists tend to be too lazy to come up with new good ones. If we're given a binary number like this one, 100000001, we have to figure out what that means in human speak. That is, what's that mean in decimal? Now, my graphics are not great here, but the general idea for binary numbers is the same as in decimal. The least significant bit is on the right, and each place to the left is 1 power of 2 greater. So this thing in the rightmost column represents the number of ones, the number of 2 to the 0. The next column over represents the number of 2s, 2 to the first power. The third column in from the right represents the number of 2 squares, or 4s. The next column represents 8s, or 2 cubed. The next column represents 16s, or 2 to the 4th. The next column represents 2 to the 5th, or 32s. The next column is 64s, and the next column is 128. So here we have an 8-digit binary number, 8 bits, and its value, if you look at it, is 128, this 1 in the leftmost column, plus 1, this 1 in the rightmost column. So this value, 100000001, is equal to 129 in base 10. Okay, so we just convert things. Now, this can, as I said, get to be a pain in the neck. Here's another 8 binary digit number, 8-bit number. And if we look at it, 1110, 0110, we can see that we have 1 in the 2's location, 1 in the 4's location, 1 in the 32's location, 1 in the 64's location, and 1 in the 128's location. So if we want to find the value of this in decimal, this is 128 plus 64, which is 192, plus 32, which makes 224, plus 4, which makes 228, plus 2, which makes 230. So the value of this 1110, 0110 is equal to 230. We have to just go ahead and map. Now, just like with decimal, just like with base 10, we can add, subtract, multiply, and divide binary numbers. Okay? So with addition, you start on the right and add the numbers in the column and then carry when needed. Okay? This is where it would be really good to have a whiteboard and some markers, but unfortunately, I don't think we have that. So we'll just walk through this. If we want to add 1010 plus 110, we will add in the right column the 1. Let's see. Hang on. Okay, we're going to try one thing. Not going to work. I thought of putting my webcam on my whiteboard here, but you're never going to be able to see me writing on my whiteboard with my marker. This isn't going to work. So we'll go back to the slides. And this one, if we want to add 1010 plus 110, you start at the right. 0 plus 0, just like in decimal, is 0. 1 plus 1 is 10. So just like with decimal, we write down a 0, we carry the 1. Now, in the third column, we have 0 plus 1 plus the 1 we carried That's 10. So we write down a 0, we carry the 1. Now in the fourth column, we just have the 1 from the top number. The bottom number, all of those leading things are implicitly 0, so there's nothing to the left of the 110. So in the fourth column, we had a 1. Adding the 1 we carried gives us 10 again. And so once again, we have the 0 with the 1. So 10, 10 plus 110 gives us 10, 000, essentially 10,000 if you wish. Okay. So binary addition works just like decimal addition. Subtraction is the same. You start doing your subtraction and you borrow from the next place when needed. Okay. 1010 minus 101. In the rightmost column, 1010, the rightmost column is 0, minus 1. Now, you can't do 0 minus 1, so you have to borrow from the left column. That gives you 10. 10 minus 1 is 1. So in our difference, the rightmost column, you have a 1. Moving to the next bit, the next binary digit, in that top number, 1010, we took out that 1. So therefore, it's now a 0 because we borrowed from that. And so now we have 0 minus 0, and 0 minus 0 is just 0. And then that leaves us 10 minus 1, which is just 1. So this is something you can do, and we'll actually show you how this works in PyChart, because Python does make this sort of nice. Now, last semester, we did put a couple of these questions on the final. I don't know if they'll be on the final this semester or not, but it's fairly straightforward. So the question is, how do you convert from decimal to binary? And I give you the actual algorithm on this slide. If I ask you to convert the decimal number 10,000,001 and ask you to tell me what it is in binary, you have to figure out how many bits you need to have. And it gives this long string on the bottom of this slide. The algorithm's there. I want to skip over to something that Python does. And so we'll go to PyCharm in a minute. Python indicates that a number is not a decimal number, but a binary number when it prefaces it with 0b. So 0b means this is a binary number. You do not want it to be the decimal number. Furthermore, if you want to convert decimal numbers to binary, okay, I've given you the algorithm for doing it by hand on the previous page. I would never ask you to do something that ridiculous on the test, by the way, because it's too easy for you to make a math error. But if I asked you to convert them, you could follow that algorithm. But you can use the built-in Python function, which is bin. Bin converts integers to binary. If you want to convert it to decimal, you just use int. So let's go over to PyCharm and play around with this a little bit. Here, we're going to say x equals 0b, which means this is a binary number, 110110. We're going to have another binary number, y equals 0b, 1001. And z is equal to x minus y. So if I wanted Python to do that math for me, and interestingly enough, z converts to decimal 45. Let's say, what is the binary of z? The answer from doing that direct subtraction is 101, 101. So when I took x minus y, I got 101, 101. Okay. Which equals conveniently from PyCharm the decimal number 45. Well, let's see whether that's really correct. What was x in integer form? X was 54. What was y in integer form? Well, I can tell you right now that y was 9. And yes, 54 minus 9 really does equal 45. So this is binary math. Now, okay, suppose that I wanted to find x times y. Okay, now 54 times 9 in decimal is going to give me 486. So I wonder what would happen if I made sure I took a binary number of x times y. You've got to multiply those numbers, and it's going to give me this long string. Okay. So when I multiplied x times y, it's a matter of multiplying column by column, carrying when needed, and that's how you get a product of two numbers. It works the same way in binary as decimal. You just have a whole lot long numbers. Now, remember, well, let me go back and cover something before I jump to that. Binary is not practical to use. I mean, other than when you're doing it actually on a machine, binary is just something that you're never going to deal with. You're going to use hexadecimal. Okay. Hexadecimal means base 16. The hex is a 6. Decimal obviously is 10. 6 plus 10 is 16. So hexadecimal numbers are base 16. And you will often hear people just say hex for short. If a computer scientist says the term hex, he or she almost always means hexadecimal, base 16 math. Now, the problem with hexadecimal is we need 16 symbols to represent the 16 digits. Okay. With binary, we only needed 2, 0 or 1. With decimal, base 10, we needed the 10 we've always got, 0 through 9. If we're talking base 16 hexadecimal, 0 through 9 is not enough. We need 6 more. So by convention, people decided a long time ago, for whatever reason, that we're just going to use the first 6 letters of the alphabet. So in order, we have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, and F. Now, in decimal form, the letter A means 10. So if I see a hex number with the letter A, that means it's 10. If I see the letter B, that means it's 11. If I see the letter C, that's 12. D is 13, E is 14, and F is 15. Okay, so when we add A, B, C, D, and F to 0 through 9, we now have 16 symbols, and we can now represent hexadecimal math. We go by powers of 16. Converting decimal to hex, this is fairly similar. There's a built-in function in Python that does the conversion for us. Now, just like binary numbers are represented by 0B, 0B means binary, hex numbers are represented by 0x. So when I say the number, we'll use A, equals 0x 14A52, that means it's a hexadecimal number. And the variable B is the hexadecimal number 0x45FF23. Okay, so these are two hexadecimal numbers. Okay, so now we've got them. A plus B, the function is hex of A plus B is going to add A plus B, and it's going to give me back another hexadecimal number. And you can see marked 0x474975. Okay, to get this, you take this 2, add it to this 3, that gives me 5. This 5 plus this 2 gives me this 7. Now this gets ugly. This A added to this F. Well, A is 10. F is 15. 10 plus 15 in decimal, we know is 25. Well, 25 base 16 is a 9. 25 is 9 more than 16. So that A plus F is 9, carry a 1. So that's why we get this 9. Now, the next column, adding them up, I have this 4 plus this F, and I carried 1. So 4 plus 15 is 19. Carrying the 1 gives me 20, 20 decimal. 20 decimal is 4, carry a 1 hex. So that's where I get this 4. Okay, this is 4 plus 15, carry a 1, gives me 20, base 16, that's a 16 and a 4, the 4 here, and I carry the 1. Now I'm back to 1 plus 5 is 6. I carried the 1 is 7. That's where I got this 7. And then this one, it's hard to see because of the spacing, but there is nothing up here. This is just the 4. So when I add the 2, that's how I get this number. So adding hex is the same as adding decimal, except that you've got to figure out in terms of powers of 16. Now, if you remember from a while ago, back in the days when we were actually meeting in person in the Interdisciplinary Life Sciences building, I think we talked about IDs, locations in memory where you would find something. Okay. And we can look those up, and those are memory addresses. And this tells you where this is. Now, it's interesting that they don't mark it as a hex number because, in point of fact, that's actually a hex number. Okay, that's actually a number, a memory location in hex, because anytime you're assigning memory in a computer, you don't go base 10 because everything is powers of 2. Everything is one more electrical switch or one less electrical switch. Okay. So that gives you the memory location. That's one of the areas where hex is relevant. Now, we got the hex function. This is what's really important, and this turns out to be shockingly easy. We have these long binary numbers, okay? 32-bit, or these days, 64-bit. If you've got a less powerful computer or maybe some phones, things are running in terms of 32 bits. Most of them these days are 64 bits. So you have a string that's 64 binary digits long, and you want to convert it to hex. This is actually much easier because you can just group the binary number in terms of 4 digits. 4 bits together represent one hexadecimal digit. Because let's think, okay, 2 to the 4th power, well, 2 to the 1 is 2, 2 squared is 4, 2 cubed is 8, 2 to the 4th power is 16. So anything I can represent in 4 binary digits, in 4 bits, I can represent in 1 base 16 hex number. So on this slide, starting from the left, 1001, well, that's an 8 plus 1 is 9. So that 4 bits together is a 9 hex. 1000, that's just 8. 1001, again, we already know that that's a 9. 0110 is 6. 1000 is 8. And 0001 is 1. So to convert the binary string into a hex string, it's just 0x989681. You can construct a very simple table, and I'm trying to remember if I put it in the slides or not. Yeah. Here is a summary of the table. We'll actually go to PyCharm and show this. Hex of 0B1111 is 0xf or 15. Int of 0B1111, you can see is 15. That's represented by the hex digit F. It's 15 base 10. So the hex of 0B1110 is E. So 1110 is E. 1101 is D, and so on. And so it's fairly easy to construct this table of for every 4 bit bit group, you have a single hex digit. Okay. Pardon me a second. So now, if you wanted to say, in some programming languages, there's Python has no theoretical maximum. But how big a number can you store in a 64-bit value? Let's try a 32-bit word first. Suppose you have an older, less powerful computer, or maybe a phone, that has a 32-bit word. You can only store 32 bits in a particular value. Okay. Now, if you're going to allow both positive and negative, the first bit has to be dedicated to the sign, plus and minus. So, for example, I want to take the integer value of 0b0. There we go. I think that's correct. And that is the largest integer I can store in a 32-bit word. It comes out to 4.3 billion, 4,294,967,000. Now, it's kind of ridiculous to show this with all the ones. Suppose I wanted to do it with I could simplify this with a hex value. This is 8 FFF. Hang on, I lost track. My apologies. Okay. If I counted correctly, this should give me the same answer, and I didn't. The binary string is one too long. Okay, that's where the problem was. All right, no problem. But to give you an example of a 64-bit computer as opposed to a 32-bit computer, suppose now I can hold 64 bits. Well, 64 bits is 16 hex digits, right? If I group these 64 bits in groups of 4, I have 16 groups of 4. So I have 15 Fs. Okay. And that's how big an integer I can store in a 64-bit word. And you can see it is a lot bigger. 783, 622, 461 million, 541 billion, 293 trillion, quadrillion. So it looks like 10 quintillion, 376 quadrillion, 293 trillion, and a bunch of others. And at that point, who cares, because it's all round off error. So in hexadecimal, you can see how much bigger, and no, I won't try to type a string of 64 binary digits. I could convert it and say, what's the binary of 0x8? And that will tell me that's what that looks like. Now, when you look inside a computer, when you actually look inside of memory, what you're really seeing is this binary number. What you're really seeing is electrical switches that are off or on, flip-flops that are in one state or another. That's what you're really seeing, and that's how a computer works. Now, you've seen some things that, let me go back to slides. Okay, this is what we've done. This slide is just a representation. It's part of the table of how you convert any 4 bits to hex.
A question.
Yeah, go right ahead.
So, does this mean that we can create a program that can be 32-bit or 64?
You indeed can.
And you just assign it in that way?
Well, normally, if you are going to be a software developer and you are specifically writing for a 32-bit or a 64-bit computer, you would do that. You would optimize your software to say, I'm only going to recognize 32 bits, right? This is the maximum integer I'm going to represent. This is the the longest word that can possibly be.
Okay.
As a general rule, unless you really are a system software developer, you won't do that. You don't need to. I mean, the purpose of Python as a high-level language is to make it so you don't need to, but you certainly can. And the people who are writing system programs, the people who are writing for speed, yes, they absolutely do write for 32-bit computers or 64-bit computers. So that's a great question. It's a great comment. Okay. Now, that's actually all the material I had today, because we're going to get in on Wednesday to sorting and searching, and that's a new topic that I didn't want to wander into much. So at this point, I have only filled up part of the class. I am willing to stay on and answer any questions you have about the homework or project, or you're welcome to leave. I will post this recording anyway. I'm not going to record any questions and answers and put them on YouTube, but I will go ahead and stay on, easily until 5:15 if you have them. And if not, you can leave, and I will talk to you on Wednesday.
Would you be able to